Okay, we will now talk about Barron's topics 9 and 10. Barron's topics 10 deals with the normal distribution, and topic 9 deals with normal distribution. Topic 10 deals with sampling distribution. So this is a run through of the basic stuff there. So first of all, the normal curve. So in this one, it says the weights of the apples in Pablo's orchard vary approximately normally with a mean of 14 and standard deviation of 5. What proportion is less than 10? And so what's happening here, it's varying normally. So in other words, the distribution looks like this. It looks mound-shaped and symmetrical, and it's centered at 14, one standard deviation above the mean. So if you go to where you're halfway down that hill, that'd be up 1.5, and so that'd be 15.5, and one standard deviation down the hill be subtract 1.5, and so that would be 12.5, like that. So there's our curve. And it could ask you, now to show your work, you just have to show normal CDF, but it could ask you to draw the curve and to show the shading. So less than 10, 10 is somewhere down here. So there's our X value, 10. So less than, that'd be drawing the curve and showing the shading, showing the scaling and everything. And so we want to find this area. So we will say normal CDF, which we've done many times this year. So less than 10, that'd be negative infinity to 10. Our mean is 14. Our standard deviation is 1.5. So to show your work, you have to go lower bound, upper bound, mu, and sigma. You got to do that every time. Now, I'm not going to do it every time in this video just for the sake of time, but you need to write LB for lower bound, UB for upper bound, mu and sigma for mean and standard deviation. And so, and of course, normal CDF is in your distribution menu, which is right above the VARs button right there. So if you go second VARs, which is distribution, normal CDF, negative infinity. So you hit the negative button, which is below the 3, not the minus sign, the negative button right there. And then just hit like negative 9999999, something like that. And so my upper value is 10. So I hit 10. My mean is 14 and my standard deviation is 1.5. Right, like that. There we go. So we hit paste and then we hit enter. And so there's the answer. So 0.00383, we shall say. And so it's, in other words, it's very unlikely to occur. So that's how we do normal CDF. You could also be asked to find the z-score. A popular thing would be to ask you to draw the curve and to find the z-score. Remember, the z-score for this value here is x minus mu over sigma. So the x value is 10. So minus 14 over 1.5. And so that would be, and so that's going to be negative 2.6 repeating. That would be its z-score. Okay. In other words, that's how many standard deviations is our value, 10, is below 14. All right, so that's that. How do you find the interquartile range? Remember, interquartile range is equal to Q3 minus Q1. And so for a normal curve, the way you can find this is just by doing inverse norm. That's the 75th percentile and the 25th percentile. So Q3 is the 75th percentile. So we'll do a second distribution and do inverse norm of 0.75. Then our mean is 14 and our standard deviation is 1.5. And so that would tell us the 75th percentile. We're using left area. And so we hit paste and we hit calculate. And so it's 15.0117. So 15.0117. That is Q3. So Q1 means to do the same thing with 0.25. Q1 is the 25th percentile. And so there it is. We go like that. And it's 12.9883. So 12.983. So you subtract those two things, 15.01173 minus that last value. And so it's so that is 2.0235, let's say. Right, like that. So that's how you find IQR. Outliers. So you remember our little formula for outliers is going to be anything less than Q1 minus 1.5 times IQR, or anything greater than Q3 plus 1.5 times IQR. IQR is Q3 minus Q1. So all you need is Q3 and Q1. So we'll say less than, and Q1, we just found that, that's 12.9883 plus 1.5 times 2.0235, or anything greater than Q3, which is 15.0117 plus 1.5 times 2.0235. This ends up being, when you do that arithmetic there, so that ends up being about 9.953. Anything less than that would be an outlier. Or anything greater than, that ends up being 18.0468 approximately. So there you go. That is how you find the outliers of a normal curve by using inverse norm. So number 4, it says the weights of Pablo's peaches varies approximately normally with a standard deviation of 2.4. One peach weighs 23 ounces and it's at the 70th percentile. What is the mean? Okay, so they didn't give us the mean. In order to use normal CDF inverse norm, we need the mean as standard deviation. So when this happens, when you're asked to find the mean, we're going to use the formula for z-score, x minus mu over sigma. So if they don't give you mu or sigma, you are going to have to do what I'm fixing to do. Use the formula for z-score, and we'll find the z-score. So the 70th percentile. So what that means is, here's our normal curve that we don't know what the mean is. We know the standard deviation is 2.4. 70th percentile somewhere up here. I mean, 70% of values are less than that. If we can find the z-score for that value, we can plug it into that formula and figure things out. Well, how do you find the z-score? By doing inverse norm with the standard normal curve. Mean of 0, standard deviation 1. We need the 70th percentile. So we go 0.7, mean of 0, standard deviation of 1. So this would be our left area. That is our mu, and that is our mu, and that is our sigma for the standard normal curve. And so let's see, and when you do inverse norm with the standard normal curve, mean of 0, standard deviation 1, it generates the z-score for that place. And so we'll do a second distribution, inverse norm, 0.7, mean of 0, standard deviation of 1, and we're going left area, and it tells us our z-score, which would be 0.5244005, giving myself plenty of sig figs. So that is my z-score, and so I will enter that into my formula. 0.5244005 is equal to, now my x value is 23. The mu, the mean, is what I'm trying to find, and then sigma is 2.4. So I'll just solve this for mu using my algebra skills. So I'll multiply both sides by 2.4. So I'll just take this number and go times 2.4 is equal to, and so that's 1.259 approximately. So now I would have 1.25856 is equal to 23 minus mu. So I'll subtract mu from both, to subtract 23 from both sides. So I'll just go that, so I'll just say that number minus 23. And so that gives me that minus mu is that. So therefore mu is equal to 21.741. That's how you do that, using the formula for z-score. So there it is. There's a run through of some basic, some of the main problems you see with a normal curve. Now, and then the next thing about that dealing with normalities, when you're asked to assess normality, okay, and you're given a list of numbers and you're asked the question, are these varying approximate normal? Now, let me say this, a sample size this small is sort of a joke to assess normality with, because there's an infinite number of points in a normal curve, and just having like 15 points like this is sort of a joke, but I just wanted to show you the technique. Basically, what you want to do is we want to see if those numbers roughly look like a normal curve like this, where it's mound-shaped and symmetrical, okay? But we also know that in any normal curve, 68% of the values are within 1 standard deviation, 95% are within 2 standard deviations, and 99.7, or basically all of them, are within 3 standard deviations. So that's what is known as the empirical rule. So we want to check that. We also want to remind you about a plot called the normal probability plot. We want our normal probability plot to be linear. So the way you assess normality is by 3 things. Look at the histogram Does the histogram look mound-shaped and symmetrical? Number two, does it obey the 68, 95, 99.7 rule? And is the normal probability plot linear? Do not make a box plot to assess normality, because you can't tell if it's bimodal with a box plot, okay? So first of all, what we'll do is we'll make a histogram. And so the way you do that is I entered the data in list one. So I went stat and edit, and there's all the numbers. I put them in list one. Now let's make a histogram. So I'll go second stat plot. Okay, only plot one is turned on. That's good. So I hit enter. The histogram is this one right there, right there. So I enter on that, and it says list one. That's good. Frequency one is that's good. Let me hit my y is equal to make sure there's nothing in there that would mess up my graph, and there isn't. So then I just hit graph and then zoom 9. Okay, that's a bit right skewed, but really it's not that bad. Okay, so our reaction to this is has a bit of a tail going to the right, a bit right skewed, but it's reasonably mound shaped and symmetrical. And especially for a small sample size like this, it's hard to judge. But the first thing you do is draw a histogram when you're asked to assess normality, and then talk about, is it mound shaped and symmetrical? And that I would say, so once again, I would say this is a bit right skewed, but it's somewhat mound shaped and symmetrical. The next thing, which is the most time intense part of this, is see if it obeys the 68, 95, 99.7 rule. So we want to see if roughly 68% of the values are within one standard deviation, 95% are within 2, and 99.7 are within 3. So we need the mean of standard deviation. So the way we find those is going stat, calculate one variable stats of list 1. And so we get that the mean of these numbers is 34.6 repeating. And then we'll use S, the standard deviation is 6.4. I'll just call that 6.48. So the mean of this data is 34.6 repeating. And if I go up one standard deviation, if I go up plus 1S, and that means I add 6. So my S is 6.48. And if I add that, if I go up one standard deviation, that takes me to about 41.15. Then if I go up 2 standard deviations plus 2 standard deviations, I would add 6.48 to that. That gives me about 47.63. If I go up 3 standard deviations plus 3S, that would take me up to about 54.11. So here's the mean. If I go down one standard deviation minus 1S, so that'd be 34.6 repeating minus 6.48. And so that takes me to 28.19. If I go down 2 standard deviations minus 2S, that would take me to 21.71. That's just subtracting 6.48 minus that. And if I go down 3 standard deviations, that would take me to about 15.23. We then count up the number of data points that are in each of these intervals. There's no values that are less than 15.23. How many are between 15.23 and 21.71? None. There's no values there. How many are between 21.71 and 28.19? Well, there's going to be 1, 2, let's see, just 2, right? Those are the 2. How many are between 28.19 and 34.6 repeating? Well, that would be 1, 2, and then 3, 4, 5, and then that would be above it. So there's 5 there. How many are between 34.6 repeating and 41.15? So you count those, and that'd be 1, 2, 3, 4, 5. Once again, how many are between 41.5 and 47.63? And so that would be 1, 2, 3. There's 3 there, and there's 0 there. So there's a total of 15 numbers. Okay. So within one standard deviation of the mean, that is these 10 values. So within one standard deviation, we have 10 of the total of 15 values. That's like 0.6 repeating. Okay. In other words, that's 66.7 percent are between. All right. Within 2 standard deviations, all of them, 15 out of 15. And so that's 1. That's 100%. Okay. And then obviously within 3 standard deviations is going to be 100% as well. And so what we would say is how close is that to the 68%, 95%, and 99.7%, 99.7. And we would say that's reasonably close as long as it's within like 7 or 8 percentage points with a relatively small sample size. We would say it's reasonably close to the empirical rule. So therefore, I feel the data is approximately normal. And then lastly, so that certainly takes a bit of work to do. The last thing to assess normality is to look at what is known as the normal probability plot, which you'd never be expected to know how to do by hand, but you can use your calculator. So if you go second stat plot and hit enter, the normal probability plot is this last plot. And the key thing is this, so I hit enter on that. The normal probability plot needs to be linear for the data to be approximately normal. We need it to be a line. And so I hit there, the data's in list 1, I hit graph and zoom 9, and that looks linear, especially for these points. These are nicely linear. These 3 tend to deviate from that normality a bit. When you look at these points, they kind of stretch out a little bit and kind of go away from normality. But we would say this normal probability plot looks linear, and so therefore we think the data is approximately normal. A bad normal probability plot would show a noticeable curve, So there it is. That's your 3 things to assess normality of a group of numbers, okay? Is the histogram, not the box plot, mount-shaped and symmetrical? Does it obey the empirical rule roughly? And is the normal probability plot linear? Okay, so that is that. Now let's talk about sampling distributions. All right, so sampling distributions. All right, let's talk about Ralph and his warehouse that's filled with lamps. So Ralph has a warehouse that is filled with lamps. Unbeknownst to Ralph, 22% of the lamps have a defect in them. So that's our population value. That's our P. That's 0.22. That is our parameter. All right, Ralph wishes to estimate the proportion of lamps that have a defect in them. So he wants to estimate that. He doesn't know what it is, but he wants to estimate that. He takes a simple random sample of 200. So that's my sample size. Describe the sampling distribution of the sample proportions among the 200 lamps. What is a sampling distribution? Well, Ralph is going to find the proportion of these 200 lamps, all right, that have defects. Now, if he takes an SRS, it means he's getting a good non-biased estimate, all right? It's going to be probably around 0.22 because 0.22 is the true value. It is the proportion of all of the lamps in the warehouse that have defects, all right? But he's taken a simple random sample of 200 of them, and there's thousands in there. He's just getting 200 of them. His sample proportion is what we call a p hat. That is the proportion of the 200 that have defects in them. It's probably going to be somewhere around 0.22, but probably not exactly equal to it just because of sampling variability. What a sampling distribution is this, is if he took another sample size 200 and found another p hat, and took another sample size 200 and took another p hat, and found many, many, many different p hats. This is what we call a sampling distribution. It's every value p hat could take in repeated sampling, okay? Every value p hat could take in repeated sampling. And anytime you get a p hat or an x bar, it's just one of many you could have gotten, and all of the ones that you could have gotten are what we call a sampling distribution. Now these p hats will be approximately normal, okay? They are going to be approximately normal because why? And our rule that you have to memorize, that you should hopefully know by now, is n times p and n times 1 minus p are greater than or equal to 10, okay? Which they clearly are, okay? So our p hats are approximately normal. So, all right, so when you're asked to describe the sampling distribution, it's just like describing any distribution. You have to cuss. You have to say, first of all, it's center, all right? The mean of these p hats is equal to p, and that's 0.22. So thus, I've described the center, all right? The unusual values, the outliers, are going to be described when I say it's approximately normal. That describes the nature of the outliers. All right. The spread is described by the standard deviation. The standard deviation of the p hats, well, guess what? That's on your that's right. That's on your formula sheet. So on your formula sheet, so you know where notice it says sampling distributions, and then it says for proportions. And so sampling distributions, the mean of the p hats is equal to p. The standard deviation, the sigma of the p hats, is equal to the square root of p times 1 minus p over n. There we go. And so that the way that would play out here is that would be equal to the square root of 0.22 times 0.78 divided by 200. And that, in fact, is equal to, according to my records, 0.029292. I like that. And so that takes care of the center, that takes care of the spread. Now the shape. The shape is going to be approximately normal. Approximately normal. Why? Because n times p. So n is 200. So it'll be 200 times 0.22. And then n times 1 minus p, 200 times 0.78 are greater than or equal to 10. Okay. 200 times 0.22 is going to be 44. And 200 times 0.78 is equal to 156. And they're both bigger than 10. Both of them have to be bigger than 10. So therefore, our p hat to be approximately normal. It gives us a big enough sample size. So that's how you describe the sampling distribution. All right, what is the probability that Ralph gets a sample portion that is greater than 25%, assuming that 22% is true? In other words, assuming that 0.22 is true. Now, 0.25, if you go up one standard deviation, it's going to be, well, it's going to be, pretty close to 0.25, but 0.25 is somewhere up here. We don't know exactly where. There's 0.25. So if you were to randomly select one of these p hats, what's the probability that the one Ralph gets is 0.25 or more, or greater than 0.25? Okay, and so we got to find the area of a normal curve. So we'll use our old buddy, normal CDF. So we would say normal CDF from 0.25 to infinity. Our mean is 0.22 in our standard deviation. The square root of 0.22 times 0.78 over 200. This is my lower bound. This is my upper bound. This is the mean, or more accurately, really, the mean of my p hats. And that is the sigma of my p hats. Make sure and label these things. And so let's see what our calculator says about that. So normal CDF, and we are going from 0.25 to infinity. Or you could just put 9 million or whatever, 0.22. And this would be the square root of 0.22 times 0.78 divided by 200. And boom. So that would be equal to 0.1529 approximately. Right like there. So in other words, it wouldn't be that unusual to happen for him to get 25% in his sample just by sampling variability. Doesn't give us reason to doubt the 22% figure if he does get 25%. All right, let's say Ralph increases his sample size from 200 to 600. In other words, all this other stuff is the same. So normal, CDF, everything else is the same. 0.25 to infinity, 0.22, standard deviation, the square root of 0.22 times 0.78 over 600. 600 as opposed to 200. Let's see what happens. So when I enter this and I just change the sample size to 600, look what happens to my p-value in essence, 0.038037. Okay, even though my sample portions was the same, now there's less than a 5% chance that that would happen. Okay, so why is that? So why is the answer in number 7 so much less than the answer in number 6, even though they have the exact same sample portion of 25%? And the reason is when you have a larger sample size, okay, you're going to have less variability in your sampling distribution. So so with a sample size 200, your sampling distribution, let's say it looks like this. So here's 0.22 and 0.25 is like, it's like right there. Okay. And there's that. But the bigger sample size, what happens is it scrunches together your p hats. And so now it's going to go like that. Like that. So now the area outside 0.25 is a lot smaller. And so the way you could word this in number 8 is this. The larger sample size creates less variability in the sampling distribution. So values a certain distance from the mean, in this case, from 0.22 to 0.25, which would be 0.03, are less likely to occur. Okay. So that is an important concept. The bigger sample size creates less variability in your sampling distribution. That's an important issue. All right. So now let's talk about means. So that's sampling distribution with a proportion. Let's talk about with a mean. The household incomes in a city of 80,000 people follow a highly skewed distribution with a mean of 60,000, standard deviation of 5,000. So we don't know if it's normal, if it's uniform, what it follows. Anyway, if you randomly select one of the households, what's the probability the income will be more than 61,000? We cannot do this because we don't know what the distribution is. It didn't say that it was normal. But then, number 10, if we randomly select 30 of the households, describe the sampling distribution of the mean of 30 households. Now, when you take a sample of size bigger than 30, your sampling distribution is going to be approximately normal. So what happens there is this. Took a sample of size 30. Now, the mean is 60,000. And since you randomly selected them, you're getting an unbiased sample. So there's 60,000. When you take a sample of size 30 and get an average, it's probably, and we call that average an X bar. Okay, this is what we call a mu. The sample, the true population value is a mu. The sample value is probably going to be somewhere around mu because you're getting an unbiased sample that's randomly selected. But it's going to vary from it. And if you took many samples of size 30, finding an X bar every time, you would get all the possible values that X bar could possibly take. And this family of X bars, we call a sampling distribution. And they will be approximately normal as long as your sample size is large, bigger than 30 or so, or if it says the population varies approximately normally. And that's what is known as the central limit theorem. The central limit theorem says is that your X bars will be approximately normal if your sample size is large, or if it says the population varies approximately normally. So describe the sampling distribution. Okay, well, since it's unbiased, okay, the mean of the X bars is equal to mu, and it's equal to 60,000. That's sort of, it's an unbiased estimator is what we say, okay? All right, so the standard deviation of the X bars, well, guess what? We got a formula for that. So sampling distribution for means down here in the middle of page 2. There, the mean of the X bars is equal to mu. The sigma of the X bars is sigma over the square root of n. There it is. So this would be equal to, so that would be sigma over the square root of n. So that's going to be 5,000 over the square root of 30. And that, in fact, is equal to, according to my records, 912.871. And it will be approximately normal. The shape will be approximately normal because n is greater than or equal to 30 by the central limit theorem, by the CLT. So that is the miracle of the central limit theorem, in my opinion, is that you can take any distribution, you can take any, even a highly skewed distribution, and make it into this nice normal curve, so we can do normal CDF and inverse norm with it just by taking a big enough sample size, and that's very nice. So if you randomly select 30 of the households, there's a probability that the mean household income will be more than 61,000. In other words, if you were to randomly select one of these X bars, what's the probability greater than 61,000? So we'll say normal CDF. And it'll be from 61,000 to infinity. Our mean is 60,000. And our standard deviation is going to be 5,000 divided by the square root of 30. I'm going to label this as lower bound, upper bound, the mean of my X bars, and the sigma of my X bars. And let's see what we get. And so we say normal CDF and 61,000 to infinity. Our mean is 60,000. And our standard deviation is 5,000 divided by the square root of 30. And so that is equal to 0.13666. So in other words, it's not, it's above 0.05. So in other words, it wouldn't be surprising to us that that would happen, that we would take a sample of size 30 and get a sample mean of 61,000, assuming that the real mean is 60,000. It's a plausible occurrence, okay? But now, so let's say this. If you randomly select 100 of the houses, what's the probability the mean will be greater than 61,000? Well, if you're now, so everything's the same, except now your sample size goes up to 100. So it was 30, now it's 100. So let me just, so it would be the same thing, normal CDF. So greater than 61,000, 61,000 to infinity. Our mean is 60,000. And our standard deviation is now 5,000 divided by the square root of 100. Okay, so I'll just second entry to do that and change that to 100. Boom. And so we get, now it is statistically significant, 0.02275, below 0.05. So that would give us reason to doubt, if this happened, we got a good random sample of 61,000, it would give us reason to doubt that 60,000 really is the mean, because our p-value is below 0.05. Why is this answer in number 12 less than 11? Once again, your sampling distribution centered around 60,000. Okay, and here's 61,000. So you go like that, and here's 61,000, 61K, 61,000. So it's like that, like 13%. But if you increase your sample size, so that's n is equal to 30. So in 60,000 and 61,000 are in the same place, but our sampling distribution now gets these x bars get scrunched together. And so the area outside there is a lot smaller. The increased sample size creates less variability. It scrunches together the X bars, okay? And so the way you'd word that would be this, okay? The larger sample size creates less variability in the sampling distribution. So getting a sample value a certain distance from the mean is less likely. That's the exact same thing what we said before with the proportions. So there you go. So that's the answer to that. Okay, and now we're going to do some two sample things. So the proportion of students at Smith High School that are taking an AP class is 0.4. Okay, the proportion of students at Taylor High School that are taking an AP class is 0.36. You randomly select 150 students from Smith and 200 students from Taylor and find the proportions of them that take an AP class. Describe the sampling distribution of the difference in the sample proportions at Smith and at Taylor. So we're estimating the difference in the proportions. So we're estimating, in essence, the P, and we're expecting the difference to be that. So our difference is, in essence, going to be, the P hat for Smith minus the P hat for Taylor. Okay. So we're estimating P sub S minus P sub Taylor, which we already know is actually 0.04, but we want to look at the sampling distribution. Okay. What is the sampling distribution? Well, the true difference is equal to 0.4 minus 0.36. And so that's equal to 0.04. Okay. So that's the true difference, 0.04. Our sample difference, though, is just because of sampling variability, it's going to be a little bit different from that, but probably somewhere around it. And if we took other samples of size 150 and 200 and found the difference again and again, it created many different differences. Many differences. All right, it would create a family of differences that we call a sampling distribution that would be centered around the true value. And so describing the sampling distribution, we must cuss. All right, so the center of our distribution is, and if you look in regards to proportions, this is in essence the mean of our differences, or P hat sub 1 minus P hat sub 2, is the true difference. All right, so the mean of our differences is just going to equal to 0.4 minus 0.36, and that's equal to 0.4. That is the true difference. The standard deviation of our differences follows this formula right here, and it goes back to adding the variances when we combine random variables. It's the square root of P sub 1 times 1 minus P sub 1 over n, and P sub 2 minus 1 minus P sub 2 over n. So it would be this. We'd do it for 0.4. It'd be the square root of 0.4 times 1 minus 0.4, which is 0.6, over its sample size, which is 150, plus, and then do it for 0.36. 0.36 times 1 minus 0.36, which is 0.64, over its sample size, which is 200. And that, in fact, is equal to 0.0524595, using a healthy number of sig figs. And so, and it would be approximately normal. These differences would be approximately normal because our n times p and n times 1 minus p's for both of these groups. In other words, 0.4 times that, 0.6 times that, 0.36 times that, 0.64 times that are all greater than or equal to 10. Okay, all four of them. Can't be just 3 of the 4. It's got to be all 4. And so that would be describing the center, the spread, and the shape, and the unusual values for that sampling distribution. All right, what's the probability that the difference in sample proportions is greater than 0.06? So if you were to randomly select one of these differences, what's the probability greater than 0.06? Wherever that is. So we will say normal CDF. So that'd be 0.06 to infinity. Our mean is 0.04. And our standard deviation is 0.05245595. Okay, and so let's find that. And so we shall say normal CDF and 0.06 to infinity. Our mean is 0.04. Oops, clear. 9999999, let's say. And so this would be 0.04. And so this would be 0.0524595. And so we would get about 0.3515. So right like that. There we go. So that's how you do that. Sampling distribution with the difference in proportions. Now let's do it with the difference in means. All right, the mean ACT score for the seniors at Central High is 24.3, standard deviation of 3.1. The mean ACT score for the seniors at Riverdale High, mean of 21.5, standard deviation of 1.7. All right, you take a simple random sample of 30 of the Central seniors, find their mean and ACT score, mean ACT score. Simple random sample of 40 of the Riverdale seniors and find their mean ACT score. Describe the sampling distribution of these differences. Well, we're expecting the mean of these differences is just going to be the difference in the population means. We're expecting this difference to be centered around the true difference. And so this would be, so when you subtract those, so that ends up being, so that ends up being 2.8, okay? And then the standard deviation of these differences, well, that follows this formula right here. So for means, there is the, for the sample distribution for means, there's our formula. It also deals with, when you subtract, when you're combining random variables, you in essence add the variances and take the square root. So that's what we would do. And so this would be the square root of, and so that would be 3.1 squared over its sample size, which is 30, plus 1.7 squared over its sample size, which is 40. And so that ends up being equal to, 0.6265647. And so, and it would be approximately normal because both sample sizes, approximately normal because our n's are equal to 30 and 40, which are greater than or equal to 30 by the central limit theorem. So I didn't leave myself enough room there, but anyway, what's the probability the sample mean from Central is greater than Riverside? Well, if the sample mean is greater than Riverside, so our sampling distribution, and this would be Central minus Riverside. So this is Central minus Riverside. Well, if Central is bigger than Riverside, that means this Central minus Riverside is positive. So it's asking the probability Central minus Riverside is positive, greater than 0. So what we would do is we would use this Central minus Riverside distribution greater than 0. So we do normal CDF with that. So normal CDF from 0 to infinity. All right, with a mean here, our mean is 2.8 and our standard deviation is 0.6265647. Now we're certainly expecting it to be, greater than 0. We're expecting it to be 2.8, okay, which is certainly bigger than 0. So let's see what we get here. So second distribution, normal CDF, and that is 0 to infinity. Our mean is 2.8, and our standard deviation would be 0.6265647, and we get 0.99. We get effectively 1. So we get 0.999996. It's approximately equal to 1. In other words, it's a virtual certainty that it's going to be greater, that Central is going to be greater than Riverside. And you sort of expect that because Central is 24.3 on average, and that's 21.5 on average. All right, what's the probability that Central will be 3 more than Riverside? In other words, what's the probability that Central minus Riverside is at least 3 more, greater than 3? Well, that is going to be normal CDF. CDF of 3 to infinity. Our mean is 2.8 and our standard deviation 0.6265647. And so let's see what we get. So it's just going to be that same, well, normal CDF. And so that's going to be 3 to infinity. And so it's that. So that would be 0.3748 approximately. And that's it. That is a quick, very quick run through normal curves and sampling distribution. So read your Barron's book. Send me any questions you have. And I hope, I wish you much success. And thanks for watching the video.